This property is very known as part of solving absolute value inequalities. It tells us that if C is greater than or equal to 0, then the absolute value of A, which is less than or equal to C, if and only if A is greater than or equal to negative C, but less than or equal to C. Take note of this statement, if and only if, which means it has a biconditional relationship. In short, we are going to show both ways, starting from this that will yield to this statement, and going back from this statement leading to that, only if C is greater than or equal to 0. So how could we do this here? We start with letting, of course, I believe there is a quantifier here that our A, which I forgot to place here, that A is an element of real numbers, and let's also include here C. They are both element of real numbers, and we can apply the important absolute value properties for real numbers. With is also with C is greater than or equal to 0. So all assumptions are already in here. But of course, don't forget that it has a biconditional relationship. So we're going to assume two ways later on. Let's just simply complete this here. Take note of the definition of absolute value. Okay? For all, let's just simply use here A, element of R, so that we will be guided later. Now, there are two ways to write the definition of absolute value. The first one is with three different statements, but of course, you can also combine the first two. So you could have here A, if A is greater than or equal to 0, because it also includes 0 here, or negative A if A is less than 0. Or you could have the third form without the equality, 0 if A is equal to 0. But again, it's part of the first statement. So let's just simply place this here so we could be guided on what are the next steps. So let's have here the first step. Suppose the absolute value of A is less than or equal to C. So this one here, we're going to show this statement to be true. That for our first portion. Okay, this means that what will happen if A is less than or equal to C? So there are two different scenarios here. The first one, okay, if A is greater than or equal to 0 per our definition, the result is A, right? Then the absolute value of A is just equal to A, which means this is just equal to A, and then it's less than or equal to C. Okay, so we have shown this already, and take note that's already the first part here. Okay, first part of what we are trying to prove. And let's have the second statement. If A is less than 0, this here, then the absolute value of A is actually negative A per definition, which is still less than or equal to C, because that's what is denoted here. Now, with this two, let me use colored black pen. This here can be rearranged, or when you multiply both sides by negative, we will have here A. Okay, this yields is the inequality symbol will be changed. Again, don't forget about the properties of inequality. We have here negative C, which could be written as negative C less than or equal to A. Please don't forget about that. We multiplied negatives on both sides, and then we will have here this form, just transferring negative C on the left-hand side. Because with this and earlier here, combining them, okay, we get this statement, absolute value of A, which is less than or equal to C. This implies the combination A, this one here, is greater than or equal to negative C, but less than or equal to C. Hence, we have shown the first part of our proof okay, this direction there. But since this is a biconditional relationship, we're going to show given this yielding to that portion there. Okay, so let's have the second statement here. Now, assume that you have here negative A is greater than or equal to negative C, but less than or equal to C. Then, this means that, what would be our first statement here? Per definition, looking back on our definition here, this definition, if you would like to, we will have it here. If A is greater than or equal to 0, then A is the result of the absolute value of A. Okay? By our definition, A is the result of this if we have A is greater than or equal to 0. Please take note of that. But of course, A is identified here as less than or equal to C. That would mean absolute value of A, which is equal to A, is less than or equal to C. And second statement here, if A is less than 0, going back here, if A is less than 0, negative A is what is our absolute value of A. So you will have, okay, you will have here then negative A is equal to the absolute value of A. Okay, but we don't have negative A here, but we can use this, okay, since we have negative C is less than or equal to A, which gives us C is greater than or equal to negative A, or we could also say that negative A is less than or equal to C. Then from this and here, we can now say, we say that negative A, which is equal to the absolute value of A here, is less than or equal to C. Okay, now taking into this consideration and only this, which are both part of our portion earlier, thus we get, okay, for this statement, A is greater than or equal to negative C, but less than or equal to C, results to the absolute value of A less than or equal to C for both scenarios. Okay, now this is now the second part of our proof, that from here we reach to that point. Okay, so since both situations are already okay, hence we conclude that absolute value of A is less than or equal to C if and only if, this is short-term method for if and only if, A is greater than or equal to negative C, but less than or equal to C for all A and C element of R, and C is greater than 0. And C is greater than or equal to 0. So this is now the end of the proof. We have shown this using the two portions of our biconditional relationship following the definition that is already given. Okay, that's all for this statement. Thank you very much for watching.